Hello everyone and welcome to the latest GraphDB webinar. My name is Yasen Stoykov and I'm part of the Ontotext marketing team. I really hope that you and your families are all okay and well, staying in home or working in the office regardless of what your situation might be. The topic today is GraphDB 9.2 supports RDF star to match the expressivity of property graphs. Few words about today's presenter, which is Vasil Momchev. He is the CTO of Ontotext and the product manager of one of its flagship products, GraphDB. He has an experience of more than 15 years in software development in various domains such as life science, pharmaceuticals, healthcare, and telecommunications. He's joined Ontotext in 2005, and since then he has managed the development of complex enterprise knowledge management solutions featuring semantic data integration, text analytics, ontology, reasoning, and graph databases. Before I give the presenting rights to him, I'd like to shortly point your attention towards a couple of organizational details. First of all, for practical reasons, you are all on mute. However, I strongly encourage you to ask us any questions via the question box in your GoToWebinar panel. This webinar is also being recorded, and the link to the recording will be added to a follow-up email that I will send in a couple of days from now. After the end of Vasil's presentation, we have planned a short Q&A session in which we will try to address all of your questions. However, in case there is no time to cover all of them, I will make sure to add answers to all of your questions in that follow-up email as well. I will also put the slides from the Vasil's presentation there as well, so you don't have to worry about that either. So, without further ado, I will now make Vasil presenter so he can start his presentation. Just a second.
Okay, hello to everybody. I can see that you can see my screen. Thank you, Yasen, for the kind introduction. I really hope that you can really enjoy the time working from home. And it's really, I'm very positively surprised to see so many attendees who wants to learn something new. So in today's webinar, I'm going to cover the topics about the RDF and the property graphs. You know that for a long time there was always different religions and two communities arguing what is better, RDF or property graphs. And with the recent developments and proposed standards, basically now the question is why we should choose and what can we just use the both things. So the RDF star is a new standard which is proposed recently, and as you are going to see in this presentation, more and more RDF database providers are really implementing it. And so in this presentation, I'm going to walk you through the modeling challenges we have seen in the years, and basically this will be like a walkthrough what are the available options, and I'll give you some recommendations in terms of ontology modeling and which approach you should use when. Okay, so let me start this presentation, and everybody who starts with RDF or any programming language usually hits this hello world example, and this is the first thing which we learn. And especially in the RDF, probably you have been probably to tons of presentation and slides where somebody introduced what is RDF. And typically it's a very simple model, and you start always like we'll use this example from Wikipedia, DBpedia in this example, where we say the DBpedia Abraham Lincoln, which stands about the Wikipedia page, is a president of United States. And this is really the short introduction. And you say, okay, there is a subject, predicate, and object. Naturally, the people say, oh, it looks really easy. Is this everything in RDF? And then the next question is, no, I'm going to give you also the black belt in RDF and give you the advanced modelings. And I'll tell you that not everything is really a RDF resource. We might not a RI. We might have also literals. And Abraham Lincoln is a language typed literal, and then the United States is another language type literal. And typically you say, okay, that's everything what you need to know for RDF. You are now experts in the modeling, and you can start from there doing complex ontology models. And this is probably the situation where every one of us started in doing this type of trying to address this type of modeling challenges. But really the problem is that, okay, these examples are really a very big oversimplification, because if we model this and imagine that United States has over 40 different persons as presidents, in one true knowledge model, somebody may ask the question, how many are the US presidents? And you're going to get something like, I don't know what is the exact number, but 40 so many presidents are currently active president of United States, which is not exactly true, because we have this type of a temporal aspect of the information. Obviously, Abraham Lincoln was a president, but he's not an active president who is serving currently. The other thing is about this, what is really the ultimate truth? And usually RDF is model which represents the ultimate truth. But we know that in most of the enterprise scenarios, this is something which hardly exists, and there are different type of information sources which are giving conflict type of information. So tracking provenance, who said this, when said it, is highly important in order to answer why we got this information in our database or our knowledge graph. And also there is always some partial context, and there are additional many type of attributes. Basically, you sometimes want to add some attributes, what was the start and date. And obviously, this type of starting examples are good for starting, but they will not teach you how to do the programming like in the real programming language. And it's a really great oversimplification. So later in this presentation, we are going to talk how to address different type of modeling challenges and what is really the pros and cons of these approaches. So let's do a reality check. What is the real challenge in representing the data? And in this case, we are going to take the information page of Wikidata, and we say, okay, let's go to Wikidata and find out about Abraham Lincoln. Who is that person, and what is really the information available for it? So he's the 16th president of the United States. Obviously, this is one of the description. And we see that now we have a slightly more precise relationship semantics. And they say, okay, there is a position held, that he is not really a president of the United States, but he has the position, which from an ontology and modeling perspective makes more sense, because he is not the president, but he is really having this position. And as every position, there is some sort of a contextual, in this case temporal information, which says that there was the start and date of his presidency, and who he replaced and who replaced him. And obviously there is also that he is the 16. This is the ordinal value, which you can see on your screen. Further, there is some provenance, which is further metadata about this type of a position held, and it gives you where this information comes from. Obviously, this is important from Wikipedia project, and there is a reference URL which is saying what was the citation in order where you found it. And obviously, we have also the date, because if you do updates of this knowledge graph, you want to know what was really the source of the fact, and to be able to update it later on. So this is really the real challenge which we face when we model real type of systems and knowledge graphs. It's really not so simple as the knowledge, as the hello world example, and sometimes you need to model such an information, even for a very simple statement. So what is really the challenge? And we are going to speak about the property graphs and these RDF standards. let's go to this the same example, and we say, okay, we say this is Abraham Lincoln, and then he had the position held. We say, okay, he's not president, so he has this position, and the role is president of the United States. There is a lot of metadata, which is not how to, the question is how to connect it. And this is not specific to Abraham Lincoln. It's not specific to the president of the United States, but this is specific exactly on the statement level that Abraham Lincoln had this position as a president, and these were attributes of the relationships. So it's not fair to connect it to any of these two nodes. And now the question is how to do this. So from a knowledge perspective, we call this NRI relationship. And we are going in this presentation to give you an overview of 6 ideas how we are doing this for various reasons. And obviously, we are going to introduce the RDF star, which is really the ability to assign metadata on statement level, like this is possible in the property graph model, and explain how this works. So before to jump into the examples, I want to give you really some sort of a knowledge representation fundamentals. And basically, we have this type of a NRI relationship where we have a position held. This is really the type of a relation. And it has multiple type of arguments, like the person, the position, start, and date. And we say this is an NRI relationship because all these arguments are like the attributes of this relation. So this is really perceived problem for a very long time in the RDF community. So there were obviously some existing approaches how you can model this using reification. This is already something part of the RDF standard. Then we were always advising some of our users to go to any relationship with a new concept. And I'll give you some more exotic examples like singleton properties, name graphs, and context objects. And obviously, what you're going to learn in this presentation, why RDF star is superior, because we are going to give you also some benchmark tests which prove that this is the most efficient way to represent knowledge. So let's go to the standard reification and also teach you how this works. Reification is really to use the language itself to express a more complex expression using the to have a more complex expression using the existing primitives. So how the standard reification work? We have the Abraham Lincoln position held president of the United States. This is what stays for this photos acronym. And the idea is we are going to create a new blank node. It's not really mandatory to be a blank node, but most frequently this is used as a blank node. And to say, okay, we are going to create a new concept, which is a statement, RDF statement. Basically, this is something which is already existing from the RDF vocabulary. And there are some standard predicates for RDF subject, predicate, and object. And the meaning of this semantic meaning is that we are going to create a new object which is going to point to Abraham Lincoln subject, position held, and photos. Basically, this is saying we create a new type of an entity by describing the subject, predicate, and object. And for this new blank node, now we can attach the start and date and all the arguments of the relation. So yeah, obviously the biggest benefit of this approach is that it's as old as the RDF 1.0 standard. So it's really a very old existing standard. And in theory, it should be supported by all stores and everybody who really knows something about RDF. You can express this because in reality, this is a plain old RDF, and there is some sort of an agreement on top of the model. What is the interpretation of RDF statement, subject, predicate, and object, and how you should really consume this type of data. Unfortunately, even after so many years, this is considered as a very bad practice to use reification, mainly because it's a very verbose way how you can express things. And even if you have some sort of an internal efficiency optimization to improve the efficiency, doing SPARQL queries with this construct is no easier. And it's always has been perceived as something which is really relatively complex and slow, because typically for one single statement, in order to attach some metadata, you need to create at least 4 additional statements just to identify which is the statement for which you want to state something additional. So this is something which you can see in some sample data sets, but for sure it's not really widely used in any type of a commercial grade type of a use case. Probably this is the most recommended way, and for all the users before GraphDB 9.2, this will be the recommended approach how we say how to do this. It's very similar to the standard verification, but it's really creating a new type of a concept in the ontology model, and we say we are going to make a new type of a concept which is position held, and this will be no longer a simple predicate, but this is a new class position held, and we will say person, position, and start date. The difference with the standard verification is that we are not using generic terms, the subject, predicate, and object, but we use some concrete type, some concrete types which are understandable for the user, and that will be much clearer. Okay, if you see a position held and you see there is one object property person and position, then it will be clear what was the intention of the author. The benefit is really standard supported by all the RDF stores. Obviously, it's still not standard RDF, but one of the challenges here is that it severely increase the complexity of the ontology. And if you really want to track for every type of a relation some additional metadata, from a simple ontology like 5 to 10 types, you can explode to maybe hundreds of types, because every type of a metadata you need to create a new intermediate node which will be able to connect the data. Also, this makes the traversal, the graph traversal, not very friendly, because all these type of relationship type of concepts, you see that they are terminal nodes. You can go to them, but every time you need to use inverse paths to get out of them and really to grow. So if you want to find a sequence, please list all the type of precedents. You need to find a position held, then to go to the person, then from this person to go to the job position of the next one, and every time you're going to switch the direction because you see that the job position points to the person and the position. So this was obviously the recommended way which we are giving to many users, and the typical complaint was that this is typically slow and difficult to traverse. For completeness, I'm going to give you other things which exist in the literature, and they are really smart ways, and I'm going to say why we don't recommend them to use them with GraphDB, although we have seen some benchmarks exposing them. So the singleton property, there was one smart person who tried to work around this in a smarter way. And he said, okay, if we have the Abraham Lincoln and position held POTUS, then I'm going to make a unique ID assigned to the predicate, and I'm going to use this local name #1. And this #1 will make it different, that the #1 is really a new type of a predicate for which I'm going to state something. So depending on the query, if I want to really see for exactly this type of relationship something, I'll use the position held and the /ID of the statement. So it's basically acts as some sort of a statement ID. And I am interested only about the position held and what is really the relation, I'm going to ignore the local part. Obviously, it's a smart way how you can work around this and put statement IDs and to encode them in the statements. But one of the challenges is that typically the GraphDB indexes are fine-tuned for a relatively small number of predicates. And in this case, if you have a lot of statements with metadata, basically the indexes of GraphDB will be increasing exponentially and the database will be awfully slow. So the other challenge is that the database will be awfully slow because for every type of a statement it will create a new page, but also you need to maintain these complex IDs somehow outside of the database and to preserve the consistency. If this statement changes, you need to delete it and to update it. Also, this is something which is fully incompatible with the inference because basically your inference schema should have basically for every statement ID something how to interpret it. So in this case, more or less, you cannot really combine it with inference with any of the existing engines. Another way how we can work around this is we know that the modern triple stores are actually quad stores, and they track additional metadata, with additional parameter, which is the context of the name graph, depends on the implementation. And the idea is really we are going to put the same sort of a statement ID, but track this as a name graph, which is going to solve many of the problems of the previous approach, where we are going to track the statement IDs for the predicate. And once we have this statement ID, ID1 on this example, we are going to say, okay, this is the start date, and we are going to maintain this in its own name graph. Obviously, the benefit here is that, once again, it's a relatively short syntax, and you can, in an abstract way, attach as soon as various types of metadata and track this independently. But obviously, the challenge is that the way we say this is you overload the graph parameter, and if you want to update the provenance of the information and to update like from these statements are coming from this file or this information source, you cannot easily do this. Basically, any update operation will go in the ID statement. I need to update another type of a attribute like the source of the information, and then every time I update a graph, I have to scan for all the name graphs which came from the source, and then to update only this type of statements. Clearly, this is a possible approach, but this will have a really high computational cost because the overload, because you cannot really efficiently use the name graph indexes anymore, not only in GraphDB but also in other RDF data store implementations. So obviously, if you don't need the name graph and everything is really coming into a single graph, and you don't need really to track what was the provenance, or the provenance is not that important, and you can pay a higher computational time, this is a really very reasonable approach which we recommend to consider. Another probably a more exotic approach is the context objects. And the context objects is something similar to the singleton property, but the idea is you're going to make a blank note which is going to abstract the actual object. So Abraham Lincoln position held, and then you put the blank note but not directly the object. And then for this blank note, you put the object President of the United States, and then you have a start date. Once again, this is a really standard RDF supported by all RDF stores, and it's a relatively easy way to track the data. Obviously, the complexity will propagate to all queries because you have to rewrite every triple pattern, that it's not a direct triple pattern anymore, but every even single triple pattern will be joined if there is a metadata for this object and you need to make this consideration for this blank note. Once again, this is a fully incompatible with the inference, and this will mess up all the rules and all the implicit statements, because the implicit statements will be basically partial, and they will be affecting these blank notes, which holds no real value here. So the context objects, I think, is something for completeness just shown here, that this is another way how to do this. And let me summarize, even RDF is a very simple model. You see that there are many ways how you can model and express information. And typically when we speak with people who are using the property graphs, this is one of the main complaints, that with these abstract models, you can abuse them in a various way how you express something. And every time you need to check a documentation and to really to spend some significant time to understand what is really the meaning of these connections in the graph in order to know how the data is really modeled and what is the meaning of the information. And that's why the RDF community decided maybe just try to reuse some of the best practices of the property graph model, which somehow considered RDF, but to simplify it and to extend the RDF with additional features in order to match all its good expressivity and to give a standard way for the users how to express complex statement level metadata. And this is how the RDF start basically proposal. It was started by one person, Olaf, who made a positional paper. In the next years, basically he struggled for many years to convince the RDF vendors that this is the right way to track provenance and metadata. And now this is becoming de facto one of the proposals for extensions in the RDF 1.2. And this is something which I hope will make it will be included in the standard, so everybody who uses RDF has a standard way to associate metadata on the statement level. So the approach is really quite simple and easy to understand. Basically, he steps on the concept of the standard verification. And if the RDF is having something as a standard verification, why we just don't simply fix the syntax and make it much easier to query everything in SPARQL? And this is exactly one of his proposals, is that we are going to introduce something as a new RDF type, which is really, he called this in his paper, embedded triple. And the embedded triples are syntactically serialized with these two brackets, curl brackets, which you see on this example. And the meaning of this will be, this is a reference to the statement Abraham Lincoln position held POTUS. So the meaning of the second statement, which is Abraham Lincoln, which has this type of an auth subject, which has a combination of subject, predicate, and object, means that this is a reference, like in the programming languages, this is a pointer to this statement, and this pointer to this statement has a start date and a specific date. So this is a syntactical way how you really can express the metadata in a turtle file or other serialization formats in order to make it understandable that you want to state for this particular statement, not the subject, not the object or the predicate, but for this particular statement, what is really the associated metadata. What are really the benefits is that obviously this is a very short syntax and it allows you simple schema evolution. Unlike the previous examples, if at some point you decide to track metadata for an existing triple, you don't have to change your model with any of the previously shown approaches. You can just say, okay, I put a pointer to this type of a triple, which we call embed triple, and I'm going to state something about this. So in general, this should reduce substantially the amount of changes of your queries because you just extend the model with some additional metadata. Okay. Some people will say that one of the models is data and another is a way of including metadata. I don't want to go in this philosophical discussion, what is data and metadata. The other benefit is the specification is giving you just the way how you should implement and serialize this. And the benefit, and some of the implementations, they might even implement this internally as a standard verification, basically to translate this type of a statement, to serialize it as a standard verification, or to use name graphs as identifiers. Basically, the standard is giving it only from a client perspective. What should be the input RDF? What should be the output RDF? It has a strong semantics and also how the SPARQL should behave. Obviously, it has some downsides since this is an extension of the RDF format. Not all serialization formats and all previous RDF stores may support this. So this is obviously the discomfort that if you once again switch to RDF star, you may limit the number of implementations supporting this. So how this really works in SPARQL, this is another aspect of how the SPARQL star works. We are going to show the same type of a statement and how we are going to query it. Once again, because the standard verification is two verbose, we can consider the position held and the POTUS of this reference to the triple with the two brackets. That this is going to be meaning this is a reference, and this reference has a start date, the predicate, and I'm going to take this as a free variable. Another feature which I want to show here is that in general, although this looks like a constant, because typically if you have something in these brackets, it's a URI, but the SPARQL and the specification, the SPARQL star and the specific in its specification allows to have this as an unbound variables where to say, okay, the subject may be a wildcard. So I want to find all subjects, all references to subjects which are unknown, which have position held, and then POTUS, and then you go the start date. So in this case, you can really retrieve this as a wildcard. And in this case, if we have voted all the US presidents, we are going to retrieve all the presidents and the day they started the presidentship. So this is basically what returns the query. The proposal is a fairly high level, and it gives you no tips on the implementation. So we are going to discuss how the different stores are implementing this. There are small variations, but typically it gives a very elegant syntax how you can do this metadata association. So we agree that there is a one single way how you should model this, and not really bother with the NRI relationships or the single tone or the standard verification anymore. So basically how this slide is going to explain how GraphDB implements this. The new features related to this type of functionalities, actually as developers, we were in the context with the author and were asking how really we should approach this. And our choice was really to add a new RDF type. You know that there were 3 pre-existing RDF types. This is the URI or the IRI. We have the literals for the string values or the numeric values. These are the data type properties. And we have the blank notes. These were the 3 types. And now we introduce a new one, which is embedded triple, which has exactly the meaning, a reference to a triple, to another statement in the repository. So it has the same meaning as the pointers in the programming languages. This is not the statement itself, but this is a reference to the statement, which allows you to associate some metadata. Why we decided to do this? Because this is probably the most efficient way how once you see these type of statements, to preserve them in the existing data structures and to have all the indexing and to improve the query optimization without doing any rewriting. And basically one statement in the input RDF is always equal to one statement in the repository. There are other implementations which are trying to mimic this with name graphs, or even may they try to convert it to standard reification. So there is another thing which was a big controversy about the specification, whether if you assert a statement with embedded triple, like in the previous example, if you state Abraham Lincoln position held POTUS start date, whether you can reference something which does not exist. Do you have to assert also the original statement that there is President Abraham Lincoln and he held the position President of the United States? Unlike the other stores in GraphDB, we decided to be fully compliant with the existing standards, and the pointers basically does not imply that you need to assert this statement. So basically, you can state metadata for statements which does not exist in the repository. This, in our opinion, this enables various ways to state, for example, to enable many use cases which we have seen them a lot, is like soft deletes. For instance, you have a triple coming from one original data source, and this data source is produced with an automatic conversion by some ETL or another data pipeline which generates them. And at some point, some of the users decided that this statement is wrong and you don't want to have it in the repository. So one way to implement this is basically to assert a reference to this statement and somebody to say, okay, this statement was deleted and we don't want it in the repository. In this case, you want to point to something which does not exist, but to have this pointer. So the next time you update the data set, to see that there are pointers to some things, to some values which you want to be deleted, so you're not going to assert them once again. Also, the other challenge is that some of the implementations, you see that this is a triple, and the question is that the underlying model is the context and name graphs. So you basically assert a statement, and if you delete the reference to the triple, you also need to retract the statement. This might be not very transparent, especially if you have context, and at some point you retract the statement, a reference to a statement, and since this is the last reference to this type of a statement, you're going to retract the statement itself. And we find this as some sort of a non-transparent and not nice way, a black box manner for a database. So basically, this type of embedded triples is like a completely new type, which has its own life, and the user needs to explicitly add it or delete it in order to manage it. Another thing we did was to extend the turtle, the trick, and the JSON, the SPARQL JSON results serializations in order to enable this type of a serialization. As you probably, some of you may not already, this type of embedded triple is not compatible with all the serialization formats like RDF XML or JSON LD, which you don't have a way to say, okay, I have a new type there, and how you should do this. So basically, GraphDB added a new MIME types, which I'm going to show as a pointer to the documentation, which says that there is a turtle star, trick star. These are new content type formats in order to enable this type of values to preserve the forward and the backward compatibility. Also, the specification allows to have embedded triples. So there is a typo, this should be embedded, nested triples. And the nested triples allow just one reference to a statement to point to another reference to a statement in order to express truly complex metadata about metadata. And for the serialization formats which do not support basically this type of a this format, the GraphDB server is going to encode the embedded triples using this schema URN RDF or J triple, and there will be a base, base 64 serialization of the value subject, predicate, and object to allow for some older clients who don't know what is really the embedded triple to still work and to see this as a statement which, okay, it's a rather strange, but this will not break the older clients to read this information and understand that there is some sort of a function there. And also, as part of the engine, we implemented a couple of SPARQL functions, actually a handful of SPARQL functions, which allows you to work efficiently with the embedded triple types to extract from an embedded triple what was the subject, predicate, and object, and so on, in order to improve the expressivity in SPARQL. So let's take one practical example, because so far we were talking only about the modeling and some abstract modeling things. I'm going to point you to one very interesting paper which was originated a couple of years ago, and it was covering the modeling approach of Wikidata and how you can do the reification of RDF and what will work well for the Wikidata. Basically, the authors took a subset of Wikidata and used various modeling approaches in order to decide which is the most efficient way in order to benchmark also different type of triple stores. And in their paper, basically they tested standard reification, NRI relationships, and name graphs. This was what they tested. And what we took was basically to take the standard reification and to convert it to RDF star in order to evaluate the performance of the RDF star. As you can see, this subset of Wikidata, which is a snapshot, and I'm very grateful to the authors of the paper that they provided it, has like 400 million statements if we model this with standard reification. As I said, this is a highly verbose mechanism, and because there are 400 million statements, the loading time obviously is the slowest one because it takes 52 minutes just to index these statements, and the repository image, this is in gigabytes, took really 36 gigabytes, 0.768 megabytes. So not surprisingly, this was the highest number of has the highest loading time and the highest repository image, although many of the URIs are repeated because you have constantly RDF statement, RDF subject, RDF predicate. This is really a lot of data just to index it as the plain old way. The second approach was using NRI relationship, and you see that it's a really better, but not that better, because the only thing what you are missing is this type of a dummy RDF statement, which points that the blank note is a standard verification. And for all the other values, you need to still do the same thing. The loading time, obviously, here is slightly better, and the repository image still becomes substantial. If we go to the name graphs, you see that the name graphs are really high optimization. Obviously, you overload the provenance algorithm, and you really substantially cut the results. And if you go to the RDF start statement, because in this data set there is a lot of nesting of embedded triples, and that's why it's even much more efficient than the name graphs, we see that the same data set nearly shrinks in half, and it has the loading time of 34 minutes. So if you have a complex model with a lot of metadata like Wikidata, you can see and speed up the GraphDB by using the RDF start with up to 40% due to the more efficient persistence of the data and these new type of indexes which are in the database, which in total decrease the total amount of statements. So here is an interesting evaluation we did. I will be glad if some of the authors of the other databases are commenting and suggesting some improvements to this table. But this is how the different stores implement the RDF star, sorry. And basically, on the top in the columns we have the different implementations. Then we have the feature, how they depend, and obviously the comparison is GraphDB supports this nested embedded triples, so they can reference this. This is only possible in BlazeGraph.do.1. The other vendors decided that it's probably not important and it will be confusing for the users if you have nesting of embedded triples. So the next is about behavior, if what will happen if you reference to a non-existing statement. And in GraphDB, as I said, we allow to reference a non-existing statement, basically to state metadata for something which is not part of the repository because of the specified use cases, and all other implementations basically are saying that if you assert embedded triple, then we are going to assert also the statement itself. Okay, the question is whether you can duplicate standard verification and embedded triples. And by the way, reference to a non-existing statement, I would say that GraphDB is really the only type of a store which fully implements the standard verification in a more efficient way and according its semantics. And now the question is it possible to assert one and the same data with standard verification and also embedded triples? For GraphDB, it's agnostic, and if you really decide to model the same information as standard verification and then to use a pointer, yes, this is possible, and both statements will live independently, and it will be up to the user to decide which of them can want to use. Obviously, GraphDB gives you some tools if you have data sets with standard verification to convert them during the import, or if you have an old client which does not support the embedded triples, query time when you extract the data to convert the embedded triple to a standard verification, and this is possible. In Stardock, this works absolutely in the same way, and they give some tools for conversion as well. The answer graph on its own is internally converting the standard verification, and if you insert something as a standard verification, it will become RDF start. And for BlazeGraph, they work also independently. So what about the backward and forward compatibility? If you have an old version HTTP client, which has on its implementation, and you hit a SPARQL endpoint, which happens to have these new RDF start statements, what will happen? In the case of GraphDB, if you really request a turtle or the old serialization standards, GraphDB will automatically return the embedded triples as base 64. All other implementations except BlazeGraph, which partially has some sort of a solution, is going just to give you the turtle. It's going to include the embedded triples. So you, as a client, you are very likely to get some weird exceptions, syntax exceptions, because the embedded triples is not allowed in the turtle, in the original turtle syntax, but only in the turtle star format we defined. And other issues, obviously GraphDB, we spent a lot of engineering efforts to master all the features and to really properly design them. So we found some weird limitations with the other stores. Maybe these are bugs or just something which they plan to improve is that in StarDoc you cannot import data with embedded triple on object position. So you cannot say something for a reference to a statement. In Ansu graph, the bind statement does not work. There is a specific how SPARQL should, how bind operator should work with bind. This is part of the RDF star paper. And obviously Blaze graph cannot return statements as variable and other things. So I'll be happy if there are other vendors to comment this table and to help us to improve it. But this is really some sort of an expectation that RDF star is still not a major standard. Let's hope that this will become a major standard. And there are some small deviations between the different RDF stores who supports it and how they do this. So I want to give you some conclusions and wrap up before to show you how to use the documentation. And this feature, basically, it's really a very powerful way how you can associate statement metadata about statements. And this is what we say that it fully supports now all modeling primitives of the property graph model. Obviously, this is becoming a standard. We know that the RDF community and working group are usually not the fastest working community. I understand why they are conservative, because this is a slowly evolving standard, but we expect sooner or later this will become part of the official standard, and this will be the natural way how the things are evolving. In terms of GraphDB and the specific how we implement it, we really want to preserve all the compatibility with the standard Reification and all the other pre-existing standards. There will be no automatically asserted triples or removed because of the embedded triples. We enable these use cases of soft deletes, saying what is the provenance of the information, that this should not be updated, and so on. And also we tested rigorously the implementation, that we have a fairly efficient implementation, which is not going to slow you down once you really import huge amounts of metadata about your statements. And obviously we point very clearly where we deviate from the original paper, because we really believe we are not implementing this exactly as the property graphs. We are still, GraphDB is still an RDF store, so we just decide to reuse the positive things from the property graph modeling and to implement them in GraphDB. Okay, and now we're really ready to evaluate its applicability to really complex use cases. I'll be happy that there will be more and more data sets using the RDF star, because this is a very natural way how you want to track the metadata about some specific statements. As a final thing, what I want to point you is the page where you can find some examples like this one. There are some examples which are saying what should be the behavior of the implementation, with some more examples for practical use cases, how this can work. I want to point you about some things about the bind and how the binds specifically work. So the bind is really going to make a search for a specific value. So if this value does not exist in the data set, unlike the other constants in SPARQL, this will basically act as a filter, and will return 0 results. So if you bind new value to the store as literal, you're going to get this as a literal. But if this statement does not exist in the repository, you're going to get an empty variable here. So there are some other details here, how you can convert standard Reification to RDF with some existing tools in the GraphDB library. And also there are some examples how you can do this with SPARQL queries. Basically, if you have a pre-existing repository and you upgrade, you can use this magic SPARQL to convert all your reified triples into embedded triples with a single atomic transactional operation. And these are the new MIME types and file extensions which we introduced in the RDF4J. Basically, this work was contributed to the RDF4J open source project also, which allows you to support the new content types which are natively serialized, the embedded triples. So just keep in mind that in order to read the embedded triples, you need to request like turtle star or trick star in order to get the values. Otherwise, the values will be encoded with URN, RDF, or J triple, and then the base 64 encoding of the data. Okay, so this is pretty much my presentation. I hope that you understand the basic modeling patterns, why we need this, and how GraphDB implements this. And I'm looking forward for your questions, comments in the remaining 10 minutes to have the discussion. So, Yasin, let's see if there are any questions from the audience.
Yes, there are a lot of questions. And I don't think we will have the opportunity to answer all of them during the Q&A sessions, but like I said in the beginning, if we missed some questions, I will make sure to add them in the follow-up email alongside with the recording.
Okay. So let me start with the questions then. Let's try to cover as many as possible in the remaining 10 minutes. The first one is this seminar recorded? Yes, clearly it's recorded. You can download the recording, share it with your colleagues. Then the next one is, okay, it's about, once again, missed some values. Okay, the next thing is, can traverse NRI relationships as classes using property chains in the ontology? So just for some context, in order to be able to visually answer this is, so the question is it possible to traverse with property paths in NRI relationships? Yes, it's possible, but you cannot really use the arbitrary length path modifiers like star or plus, because you need every time to change the direction of the relationship and to do a complex property path. Basically, you say I search for this type of a path, then I search for the inverse property path, then I search for this one, and this is a group with plus, which is not really the nicest and the most natural way how the people do this. So let's say there is a hack how you can do this with relationships, but this is not really the way, very usable and user-friendly way. So you don't get a certificate. So the next question is really interesting. I'm working as an academic institution. Do I get a certificate for participation? Obviously, we can give you a certificate for this participation, but the basic idea of this webinar is really to give you preview some of the new features and to really train you how to model your data. So yeah, sorry if you had really wanted to get a certificate in your CV. So the next one is a more philosophical discussion is necessary. I agree, yes, basically this may be a topic of a different webinar, like what is data, what is metadata, but just to cover slightly this type of a discussion, the question is, should I use, for example, one of the common question is, should I model my data like start and date as a metadata with embedded triples, or I should model this as NRI concepts? My recommendation and the most typical way how Wikidata will do this, and probably Ontotext, is that we're going to model the President of United States in the ontology model, because this is a really concept which should be very clear for every user of the model, that President of United States position is really a kind of a position with a start and time in order to enable inference and other interesting things. And some metadata like the reference and where this information comes from, probably I would model in a default scenario as embedded triples, because this is a metadata which probably should not be exposed for every user and only the people who are interested about the statements. So I know that this may trigger a huge discussion and polemic about what is the right way, but I'm just sharing some practical insights what you should experience. Okay, the next thing is, should be president wildcard position held POTUS, instead no. Maybe there is a typo, I don't know. Let me see. Okay, yeah, I'm really happy that somebody noticed this, and there were really very attentive people in the audience. Yes, obviously the correct SPARQL here is a president, so this should not be this variable is the same as this one, and it should be joined. I'm really happy that those of you who were very paying attention to all the examples. So the next one is, would this apply to the position held CEO? I guess this is some sort of a joke, which probably I cannot understand here. The next one is, hi, how to express in RDF star if a president was selected twice? So there should be two identical subjects. Donald Duck position portal start date and Donald Duck position start. This would lead to a mess. Okay, it's a very good point about saying what will happen if one person is really a president multiple times. So obviously, nothing prevents you to associate to have really one pointer with multiple start dates and end dates, and it will be up to the reader of the model to fully understand what is the meaning and how they should reconstruct the start and the end positions, because in this case the start and end date of the two presidentships will be basically mixed. I agree that using this, and if you really decide to model this with two different variables, you can really mess up. But to go back to the previous example, probably in this particular example, I would model with any NRI relationship the position held. And in this case, we are going to model this with position 1 and position 2 in order exactly to separate the start and the end date. So yeah, this is a fair point. The next thing is, what is the complexity of RDF star? You say it efficient. How efficient? What effect does it have on reasoning? Are there reasoners that are compatible with this? Okay, it's another fantastic question. I hope that probably this question was asked during my presentation. This is for one particular data set, which is Wikidata. What will be the efficiency? And the efficiency is measured in terms of smaller data set and with less triples to say the same type of knowledge, to express the same type of knowledge. And currently, the reasoner, the Ontotext, the forward chaining reasoner, is going to ignore all the embedded triples. So basically, the embedded triples, the pointers to triples, they will not participate in the inference. This is not a design problem. We can unlock this, but the rationale why we decided that for now we want to keep away the embedded triples from the inference is that some people may decide to use same as and to say this pointer is the same as to another pointer, which will be also a messy thing. So we started conservative, and if you have really a good use case about why you want to reason with the embedded triples, we'll be more than glad to enable this and to really expose it in the next GraphDB versions. So the next thing is the conceptual model that RDF star captures is confusing. The triple idea itself prevents us to treat the subject, predicate, and object as first-class objects. Hence, we get all the complications, epicycles, triples with embedded triples. Okay, I guess this is really a person coming from the property graphs. Obviously, yes, I wouldn't say that like in every abstract model, it's relatively easy to express some nonsense things. But on the other hand, the big advantage of RDF are really the global identifiers, the information schema, and I don't think that you can get really close to anything like this in the property graph model. So basically, I don't want to really go in this discussion about RDF against the property graph model. Obviously, we acknowledge the existence of the property graph models, and I believe there are good use cases for this. But yes, RDF star is really a way how you can minimize and easily express the metadata, and it's not going to solve, basically, it's not going to solve all the knowledge representation challenges. Wikidata model lets you treat subject, predicate, object as first-class objects. Actually, strictly speaking, Wikidata are using some sort of their own custom way of reification. If you go to the Wikidata mail list, you can go in this philosophical discussion whether this is a reification or not, depending of the different people. Okay, I just take the last question with a couple of more. Please please implement embedded triples for GeoSparkle functions. Okay, it's a nice one. Okay, sorry. Actually, I see that we are only half of the questions here. Thank you for all these questions. Please, Yasen, send me in order to write them in a written form and to send it to you. So I really wish you a very pleasant end of the day or start of the day whenever you are located, and just stay safe. And I wish you to speak again for the next releases of GraphDB. So bye from me.
Thanks, Vasil, and thanks to everyone who participated in this webinar. You can expect the follow-up email with the recording and the questions and answers probably on Monday or Tuesday next week, so stay tuned for that. With that, thank you for your attention and have a nice day or evening. Bye-bye.